Are the causes, mechanisms, and effects of earthquakes well understood? Hopefully, we have clearly answered this question. Where are earthquakes and volcanic eruptions likely to occur? We have also answered this question. We provide an earthquake hazard map here to summarize our answer. In this World Earthquake Hazard Map, you'll see that red areas have the highest hazard. Examples of regions with high-risk earthquakes include the west coast of South America and the Middle East. Gray areas have the lowest hazard, so this may be where you would want to go. Yellow and green areas have a moderate to low hazard. Mankind is always seeking fertile areas for agriculture, fisheries, good weather, energy, minerals, and more. These areas often conflict with the World Earthquake and Volcano Hazard Map. Here is why. Volcanic lands are very rich, especially in tropical areas, which we're known to like in society, yet very risky for volcanic eruptions. Offshore oil and gas that we use are under the control of coastal states and countries. Some of these areas are often boundaries of plate tectonics, therefore subject to frequent earthquakes and even volcanoes. Fisheries and good weather are very attractive to mankind and society alike. Yet, these are also dangerous areas to live in because of the hazards of earthquakes. Examples of safe places to stay clear of earthquakes are the following: Central U.S., East Coast of U.S., Canada, West Africa, Scandinavia, Scotland, East Coast of Brazil, and Poland. How about paleoseismicity? Northern Europe is classified as a relatively stable continental region, where seismic hazard is low. Until recently, no one would have suspected that the normal faults related to graben structures in the lower Rhine embayment could produce large earthquakes. Yet, on April 13, 1992, a 5.3 magnitude earthquake struck the city of Roermond in the Netherlands. An earthquake on October 18 in 1356 destroyed the city of Basel, Switzerland, and damaged large parts of the Upper Rhine Graben. The Roermond earthquake has raised questions about the classical approach of developing seismic hazard assessments based solely on historical and instrumental seismicity catalogs. In addition to seismicity, a comprehensive assessment of seismic hazards requires the identification of active faults and an analysis of the seismic cycle. That is paleoseismicity. Let me repeat this. In addition to seismicity, a comprehensive assessment of seismic hazards requires the identification of active faults and an analysis of the seismic cycle. That is paleoseismicity. Let's now turn to earthquake prediction, meaning the ability to predict the time, location, and size of the next earthquake. Long-term forecasting is feasible with significant uncertainty. In some cases, the uncertainty is 50 years and even 100 years. The basis of these predictions are the combination of plate tectonic theory and the mapping of active faults. recurrence intervals, that is, average time between successive earthquakes. What is not yet possible is the short-term predictions. In other words, we cannot yet tell a year, a month, or even a week ahead of time that an earthquake will occur at location A. However, the detection of tsunamis associated with earthquakes are possible and are improving. How do we stop a tsunami in the Indian and Pacific Oceans from having a huge death toll next time? We could evacuate coastal areas every time there is a potentially tsunamigenic earthquake, tsunami sirens, teach people how to respond in the event of a tsunami, recognize some of the precursors such as an earthquake or a sudden reduction in sea level, deployment of a tsunami monitoring system, a pressure recorder on the bottom of the sea. When one of the instruments senses a tsunami wave overhead, it will send acoustic signals to a buoy at the surface, which will relay the warning via satellite to officials who will sound an alarm. Buoy communicate readings via satellites. The DART-2 system consists of a seafloor bottom pressure recording system, capable of detecting tsunamis as small as 1 centimeter, and the moored surface buoy for real-time communications. DART-2 has two-way communications between the BPR and the Tsunami Warning System, or TWC. The two-way communications allow the TWCs to set stations in event mode in anticipation of possible tsunamis, or retrieve the high-resolution or 15-second intervals data. Let's talk about short-range volcanic eruption predictions. Moving magma and volcanic fluids cause earthquakes. Earthquake activity always increases before an eruption because liquid magma, hot fluids, and gases are less dense than the surrounding rocks, so they force their way through the crust to reach the surface. Let's repeat this. Moving magma and volcanic fluids cause earthquakes. Earthquake activity always increases before an eruption because liquid magma, hot fluids, and gases are less dense than the surrounding rocks, so they force their way through the crust to reach the surface. Most volcanic earthquakes are less than 3 magnitude, are shallower than 10 kilometers, occur in swarms or in lots of earthquakes close together. So the good news is that we can make predictions about volcanoes which are likely to erupt by monitoring seismic activity. We can also predict when the volcanoes will erupt. Let's now talk about shielding ourselves from earthquakes, besides staying away from buildings and other man-made structures. If we cannot predict earthquakes, we can at least learn how to shield ourselves from them. Because the collapse of buildings is the #1 killer in most earthquakes, this question then comes down to shielding buildings from surface waves. Remember that surface waves cause most structural damages associated with earthquakes. Surrounding buildings or constructing buildings with metamaterials is one way to go about shielding ourselves from earthquakes. In this photo, you'll see a destroyed building in Nepal after the 2015 earthquake. Let's talk more about metamaterials. Metamaterials are artificially assembled materials with unusually effective physical properties, such as negative elastic moduli, which may hinder the wave propagation of surface waves, for example. The engineering of metamaterials is at the earlier stage, but in this decade, their manufacturing may become routine. Here is one scenario of protecting an existing building from earthquakes. It consists of surrounding the building with a ring of metamaterial walls. As we mentioned earlier, Earth provides us energy resources such as oil, gas, coal, and geothermal energy that we need to better our lives. Yet, Earth can also kill us even more frequently these days. Earthquakes and volcanic eruptions are the major sources. Moreover, the Earth's reaction to energy production can also produce earthquakes, which can shake us severely and can cause damage to property. The earthquakes associated with energy production belong to a broad category of earthquakes known as induced or human-caused earthquakes. Sources of induced earthquakes include the injection of large amounts of fluid in the subsurface and the withdrawal of large amounts of fluid from the subsurface. The injection of municipal and industrial waste into the earth can also cause earthquakes. Here are two specific examples of induced earthquakes. Geothermal energy production involves capturing naturally occurring hot water and steam in the subsurface and converting them to electricity. About 99% of the solid Earth's volume has temperatures greater than 1,000 degrees Celsius. In other words, geothermal energy resources exist because of the substantial heat in the Earth related to the temperature increase with depths below Earth's surface. Hence, the geothermal resource base is very large because of the large volume of solid Earth at high temperatures. In some cases, steam or hot water is extracted from naturally occurring fractures within the rock in the subsurface, and a cold fluid is injected into the ground to replenish the depleted fluid. In other cases, we have to fracture an otherwise impermeable rock containing hot water. When the hot water reservoir lacks sufficient connectivity through natural fractures, the reservoir is fractured by using high-pressure fluid injection in order to increase permeability and therefore to facilitate fluid movement through rock, just as with the hydraulic fracturing of tight oil and gas reservoirs. The high-pressure hydraulic fracturing associated with geothermal developments can cause earthquakes that are large enough to be felt. One of the most famous examples is the 2006 Basel, Switzerland induced earthquake. More than 3 million gallons of water were injected into the ground to fracture a rock containing hot water at 5 kilometers depth. A magnitude 3.4 earthquake struck Basel after more than 3 million gallons of water were injected into the rock formation in this location. This earthquake was followed by 3 more events with magnitudes greater than 3. The project was immediately suspended and ultimately abandoned after 3 years. Yet seismic activity continued and is likely to continue for a long time because of the complex system of fractures in the ground. Let's repeat this. A magnitude 3.4 earthquake struck Basel after more than 3 million gallons of water were injected into the rock formation in this location. This earthquake was followed by 3 more events with magnitudes greater than 3. The project was immediately suspended and ultimately abandoned after 3 years. Yet seismic activity continued and is likely to continue for a long time because of the complex system of fractures in the ground. The second example is related to oil and gas production, or more precisely, shale gas production. Recently, several seismic events have been felt and reported by local residents in the United States in areas where natural tectonic seismic activity is uncommon, and where shale gas development and production are ongoing. So far, none of these events have resulted in loss of life or significant structural damage. Yet, they have raised public attention and concerns about the potential link between these events and shale gas development and production. To add perspective to this issue, we describe in here the recent earthquake history in 3 states of the United States with large shale gas development and production projects, including Texas, Oklahoma, and Ohio. Notice a sudden large increase in the number of earthquakes in the last 14 years compared to similar previous periods of time, especially in Texas and Oklahoma. Most of these earthquakes have a magnitude smaller than 5. Therefore, they are not damaging. We can use the spatial and temporal proximity of the earthquakes in shale gas development and production in these tables to infer a correlation between these earthquakes and shale gas development and productions. Basically here, we are dealing with previously aseismic regions, which are now experiencing a larger rate of occurrence of multiple earthquakes compared to their historical rates. The shale gas development and production projects in these regions may probably be caused by tectonic changes. Again, we described here the recent earthquake history in 3 states of the United States with large shale gas development and production projects, namely Texas, Oklahoma, and Ohio. Notice a sudden large increase in the number of earthquakes in the last 14 years compared to similar previous periods of time, especially in Texas and Oklahoma. Most of these earthquakes have a magnitude smaller than 5. Therefore, they are not damaging. However, the results in the tables do not represent scientific proof of a correlation between earthquakes in these regions and shale gas development and production projects. Moreover, the variations in the occurrence of multiple earthquakes suggest that even if such correlations may exist, they will depend on the local tectonic conditions. Even more importantly, we do not yet know the potential long-term effects of large increases in the rate of these occurrences. We generally think of an earthquake as setting off a tremor. This is not always the case, and actually may never be the case. A number of earthquakes correspond to setting off multiple tremors near simultaneously. Here are two examples. As we mentioned earlier, on the morning of September 19, 1985, a magnitude 8.1 earthquake struck some states of Mexico, including Mexico City, causing the deaths of at least 10,000 people. The earthquake was felt over 825,000 square kilometers, as far away as Los Angeles and Houston in the United States. The earthquake actually occurred in the Pacific Ocean, a distance of more than 350 kilometers from Mexico City, in the Cocos Plate subduction zone. As you can see here, the Cocos Plate pushes against and slides under the North American plate, primarily along the coast of the Mexican states of Michoacán and Guerrero. Let me repeat this. As you can see here, the Cocos Plate pushes against and slides under the North American plate, primarily along the coast of the Mexican states of Michoacán and Guerrero. It was later discovered that this earthquake was a two-event phenomenon at two epicenters, the second movement occurring 26 seconds after the first. So there were essentially two nearly simultaneous earthquakes. Because of the interference of these two events, the ground shaking lasted more than 5 minutes in places along the coast, and parts of Mexico City shook for 3 minutes. In our second example, recent studies show that the earthquake of September 29, 2009 in the South Pacific was another nearly simultaneous event. That morning, a violent temblor shook the South Pacific seafloor near the islands of Tonga, Samoa, and American Samoa. The earthquake stirred up tsunami waves that quickly pummeled the islands. Nearly 200 people were killed, most of them in Samoa. The deadly quake was the largest anywhere in the world that year. But new studies indicate that the event was even more violent than initial estimates, and that it comprised 3 temblors about 50 kilometers away from each other. A magnitude 8.1 quake was followed within minutes by another pair. If the analyses are correct, then the 3 largest earth-shaking events of 2009 occurred within minutes of each other in extremely close proximity. Let's observe that the notion of nearly simultaneous earthquakes is different from the notion of foreshocks and aftershocks. The time scale of foreshocks and aftershocks with respect to the main shock is very different from the time scale of nearly simultaneous earthquakes. Let's close these lectures on earthquakes and volcanoes with these 3 big questions. There is a large network of fractures and faults of various sizes which cross the Earth's crust. This network is central to the occurrence of potential natural and induced earthquakes. Under the right conditions, any of these faults or a network of fractures can lead to earthquakes through slippage. Can we map or image this network? What is the connectivity of the elements of this network in terms of tectonic stresses? The answers to these questions will very likely bring us closer to the short-term prediction of the earthquake. What are the possibilities that one or more failures of this network can trigger a chain reaction of near simultaneous earthquakes? Please remember At the end of this video, there will be a large number of exercises. Also remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of earthquakes, volcanoes, climate, and energy. Thank you for your attention and good luck!